Yes, so good morning, everybody. So today we have Geoff, who's going to give a Blackboard talk. So I'd like to ask you to come a little bit to the front because otherwise you will not be able to see that.
So, thanks very much. So I should say this is not the most prepared talk I've ever given in my life. Any complaints should be directed to Juan for asking me to speak fairly last minute. The actual problem is me not really being very organized about preparing it. So the goal of this talk is to explain how to derive the page curve. And the page curve can mean two different things in physics, because Page really considered two different problems at the same time in one very cool paper. The first is the page curve for Hawking radiation from a black hole, and that's really what this talk is going to be about. But the other thing, of course, that it can mean is the page curve for a hard random state, looking at a subsystem and how its entanglement entropy changes with the size of the subsystem. And probably, at least for the non-high energy people in the audience, that will be a more familiar computation. So I'm actually going to start with that computation because what we're going to see is that the two computations are very closely related, much more closely related than maybe Don Page would have thought in the early 1990s. So let's start with how to compute just the entanglement entropy of a hard random state split into two subsystems. And the really key result we're going to need for this is just this very simple statement that if I take n copies of the same state and then average that over all states with a unitarily invariant measure, then that operator is symmetric under permutations of invariant under permutations of the n copies, and so yeah, but it's proportional, in fact, to a projector on the symmetric subspace because it's otherwise invariant under unitaries. So that means it has to be proportional to just a sum over permutation operators. So these operators pi I are all possible permutations of our n copies of our state, and we're just summing over them. And then if we've normalized our measure so that we're really averaging over states so that the integral of d psi is 1, then this thing, the right-hand side should have the same trace as the left-hand side. The left-hand side is just a projector onto a single pure state. So it should have trace 1, so we just divided by the trace. Okay, so this formula should be very familiar to some people in the audience, but it's pretty simple to understand. In particular, the simplest case, sort of non-trivial case of all, is when n equals 2. And in that case, the only permutations on two copies of a system are either just the identity, you leave the two copies the same, or you just swap them over. Okay, so it's proportional to the identity plus a swap, divided by the trace of the identity plus a swap, which is the trace. If the Hilbert space dimension of psi is d, the trace of the identity on two copies is d squared. The trace of the swap is d, so it's d squared plus d. Okay, great. So let's use this to compute not the entanglement entropy of a reduced density matrix of psi quite yet, but something simpler to compute, which is just the purity trace of rho a squared. Okay, so rho a is a reduced density matrix, so we just take ket psi bra psi, and then we trace over b, closing this loop. We take two copies of that, we multiply them together, and then we take a trace over rho a. And so graphically, it's described in this way, an integral over psi over some little simple tensor network-like object, tensor diagram. Okay, so now let's plug in this formula here. So we have two terms. We have a 1 over d squared plus d out the front, but I'm going to assume d is big, so we can just ignore this second piece. So we just have a 1 over d squared, splits into dA squared times dB squared. And we just now, this is going to represent the identity, so let me draw lines connecting things as they were here. So we had our two copies here, and we're just going to connect them up, the identity. And then the second thing we can do is we can swap the two copies. So here gets connected to here. First copy gets connected to the second copy. And the second copy gets connected to the first copy. OK. OK, so now we just have some closed loops. They just give us factors of d for each closed loop, depending on the size of the subsystem. So on the left, we have one A loop, so that gives us one factor of dA. We have two B loops, so that's two factors of dB. We have a 1 over dA squared, dB squared out the front. So the final answer for that first term is just 1 over dA. And then in the second term, we see that we now have two A loops and only one big B loop. So that gives us a final answer of 1 over dB. And it's nicely symmetric between A and B, as we would hope, because in fact, this thing is by definition equal to the expectation of trace of rho B squared, which in turn is the expectation of just take two copies of psi and swap either the A subsystems or the B subsystems. Okay, it's manifestly that it doesn't matter which one we do. Okay, so that's simple enough. What about if n, we do the same thing, but for some integer n that's in general bigger than 2? Okay, so it's the same calculation, except we have, rather than two copies of psi, we have more in some big circle. Yep. Was there, sorry, okay. Yeah, any questions, please do shout, by the way, but I think we're probably in relatively familiar ground right now, so I'll otherwise move moderate speed. And in this case, there's a lot more permutations. In general, there's n factorial permutations. There's a load of them that are just going to be suppressed by factors of d and dA, dB, and we'll always assume that that's very big, so those can be ignored. But in general, it's a bit more complicated than we had just here. But there's two cases where it simplifies, and there's just one dominant permutation. That's when one of the dimensions is much bigger than the other. Okay, so if the B dimension is much bigger than the A dimension, then it's always going to be good to have as many B loops as possible. Okay, how do we maximize the number of B loops? Well, we basically set the permutation to be the identity so that each of these n B loops just get connected up and none of them get intertwined, because that would reduce the number of loops. Okay, if we do that, then we also have to connect the A's in the same way. So we end up with just one big A loop, and we get an answer. So we have dB to the n in the denominator cancels out with the n loops, but we only have one A loop, so we get 1 over dA to the n minus 1. Okay. The other case, of course, is when I did the same case in both. So the other case is when dA is much bigger than dB. And in that case, we want to maximize the number of A loops rather than the number of B loops. How do we do that? Well, we need to connect sort of this ket up to this bra. Ooh, there's a dot, dot, dot there. But for example, this ket needs to be connected up to this bra, and so on. And then eventually this bottom one needs to be connected up to the top one. Okay. If we do that, then what we find is that the B's are all just connected up in one big loop. My diagram, the way I've written things makes it look asymmetric, but it really is symmetric with the situation where B was much bigger than A. So this will give us an answer of 1 over dB to the n minus 1. So to a first approximation, we can say that this thing is just going to be given by whichever is larger out of these two. Okay. In general, that's obviously not going to be exactly correct. For example, if dA is equal to dB, then these two terms will be equal, and so they need to be added together. And in fact, there'll also be a load of other permutations that grows with n, number that grows with n, that will also give exactly the same answer. But up to some potential order 1 factor at the front that only really shows up when dA and dB are very close to each other in dimension, maybe a qubit or two different at most, then this is the right answer. Okay, great. So now that we've computed this for all integer n, if we are willing to be a bit hacky, then we can sort of easily compute the expected value for the entanglement entropy, S of rho A, because the entanglement entropy is just minus trace of rho log rho, and by L'Hopital's rule, that's equal to the limit as n goes to 1 of the expectation of trace of rho to the n divided by 1 minus n. Okay, so if we just consider these two cases separately, each of these formulas as some nice analytic function of n. We only computed them for integer n, but we can just assume that the simple, nice analytic continuation works, where we just take this power law and make n non-integer, and then it's easy to tell. This is going to end up giving us an answer of a min of log dA log dB. Okay. Great. So if you look right up to the top of the board, and it's a very stiff board, so I think I'm not going to take it down. I'm just going to point up there. I just made a few comments about this calculation that will just be important for when we come to think about black holes. So the first is, as I said, that this formula is only really highly accurate when one of dA and dB is significantly bigger than the other by a large, parametrically large factor. Otherwise, more permutations contribute, and it's a bit more complicated story, but you can still do it. There's nice tools for understanding how to do this. The full curve is well understood. The second thing is that this calculation was remarkably simple, right? We really didn't need very much here. I assumed nothing except for some very basic representation theory, and we got it in a pretty trivial calculation. On the other hand, if we tried to take some specific typical state, compute its density matrix rho A, and then plug that into trace of rho A, log rho A, that would be a bit of a nightmare to do. Right, so density matrices are exponentially large in the number of qubits. They have d squared dimensions, and each of them in general would need to be computed to exponential precision in order to get a good answer for the entropy. It would just be a horrible thing to do. But magically enough, we don't even really need to do it as long as we're willing to take some tiny probability of having a significant error, because this entropy is what's called self-averaging. So almost all states will take some value very close to the typical state. The way we know that is that there's an obvious bound that the entropy of rho A can't be bigger than log dA or log dB, because that's what you get if rho A or rho B is maximally mixed. And so you can use some sort of Markov bound that if the expectation is very close to some bound, then it almost always has to be close to that expectation. Okay. On the other hand, as I said, when dA is much bigger than dB, then the density matrix rho A itself is very much not self-averaging. If I take two random density matrices, they'll be almost orthogonal. And even if I compare them to the sort of average density matrix, where I just take the density matrix and then average over psi just for that, which is just the maximally mixed state, then any density matrix on A that is allowed will be very close to orthogonal to that. But finally, then going back the other way again, if we just looked at individual matrix elements of row A, if we didn't want to sort of characterize the whole density matrix and get it highly accurate with respect to the trace norm, then we find that it is self-averaging. So in general, any density matrix element in the computational basis, row A ij, will be equal to 1 over dA delta ij. That's the self-averaging answer, or the average density matrix answer, plus some correction that's order 1 over dA dB. So it's suppressed relative to this self-averaging part by the dimension of d. Okay. So all of these going to be playing role with the rest of the talk, where I'm just going to try to show you guys how to do the sort of analog of all of these calculations for a black hole. And we're going to get exactly the same set of things that we just got. We're not going to understand how to compute the actual density matrix of Hawking radiation. That's going to be hard for the same reason that it's hard for a typical state. But we're going to be able to compute all the self-averaging quantities. Okay? Okay. So my plan is basically to start with a very, very heuristic picture of what an evaporating black hole looks like, and to sort of understand where these results are going to come from, and then we'll gradually make things more precise, and we'll just sort of see how far we get. I will become progressively less prepared as we go along, and we can see. So let's see. I'll try to leave things up for the moment. Okay. So here is a very heuristic picture of a black hole. We have so this is meant to represent just a slice of space through a black hole. I'm not going to worry about time yet. I'm going to take a lesson from Douglas's talk and try to represent an animation. But mine are going to be drawn live, so they're going to be rather worse. So we have space far away from the black hole. Then space just looks flat. And then there's sort of some region where it starts to get very curved. And there's the horizon of the black hole here, where nothing's able to get out of. And then somewhere at the bottom of this, we have some sort of star. Okay, so one difference with the black holes Douglas was showing is that his black holes are what's called two-sided black holes, which are interesting mathematically for us to study, but do not physically exist in the universe. This is what the sort of black holes that exist in the universe look like. They were previously a star, and then that star collapsed, and somewhere at the bottom of the black hole, there's still that collapsing star, depending on how you define space. Okay, so in all this space, we have quantum fields. And a general statement about quantum fields is that quantum fields close to one another are entangled with one another. So if we look at quantum fields, just say very slightly outside the horizon and very slightly inside the horizon, then they'll be entangled. Nothing to do with black holes, just a statement about quantum field theory. Okay, now let's start our animation. Let's evolve forwards in time a little bit. What's going to happen? Well, these fields that are just inside the horizon are never able to get outside, so they're still just sort of sitting there. But the quanta that were just outside are able to escape off to infinity. Maybe this is electromagnetic field, so they propagate out with the speed of light. And so it's ended up far away from the black hole over here. Okay? And because everything's unitary, then they're still going to be entangled with one another. So I'm going to draw a little dotted line here. So that represents entanglement. So now something very different has happened compared to what would normally happen in just flat space quantum field theory. We've now ended up with very long-range entanglement that's got stretched out across the universe. Okay? And there's a general statement that just in windless space, Rindler modes close to one another look like they're in a thermal state. Those Rindler modes actually end up just looking like Minkowski modes far away from the black hole when you evolve forwards in time because of the way the black hole, the general relativistic dynamics works. So this actually just looks like thermal radiation going far away from the black hole. This is the famous Hawking radiation of the black hole. Okay, great. So now let's evolve forwards a bit more in time. So the more we evolve forwards in time, the sort of closer and closer together modes can have started and still end up getting stretched out across the universe. So basically, you start getting more and more Hawking radiation coming out. You end up with all these quanta surrounding it, all of which are going to be entangled with the inside of the black hole. And these Hawking quanta are carrying energy, so the black hole has to get smaller. Okay, and so that means that as we evolve forwards in time, this sort of interior of the black hole gets bigger, it gets longer, but its connection to the outside world, the horizon, gets smaller because the black hole has lost mass. And eventually, if we naively extrapolate forwards, this black hole turns out to get hotter and hotter. But so eventually it becomes Planck temperature and you sort of lose control of what's happened. But roughly, a natural guess is that just the black hole evaporates off entirely. And at least in a naive semi-classical picture, you're left with just some interior of the black hole that's just got completely pinched off. I'll put a this means some weird stuff happened here that at the end that we didn't really understand. Quantum gravity came into play. But basically, we're just left with a load of radiation in a thermal state that is entangled with whatever happened to the interior of the black hole. Okay, so on. Okay, so let's just compare what's happening here to what we saw for a typical state. Okay, so the first thing to note is that this Hawking radiation that's coming out is not in a maximally mixed state. So already, like a couple of qubits in, we're in a handful of Hawking quanta have escaped. We're already seeing something that's very different from a truly typical state. But this is just sort of for a boring reason that this typical state model didn't have any notion of energy conservation or entropy depending on energy. And if you do a slightly more realistic model of some typical state in a microcanonical ensemble, then you'll indeed see that if you look at random qubits of it, then they'll look thermal rather than maximally mixed. So that's not an interesting difference. That's just that the true hard random typical state model was a bit crude. But there is, of course, another difference, which is here we just continue to have more and more thermal radiation, where the radiation is correlated with the interior of the black hole, but it's never correlated with any other radiation. So its entropy just goes up and up and up. And we're just left with seemingly no black hole left anymore, or the black hole's disconnected from the rest of space-time at least, and just this cloud of thermal radiation. So this is very different from the typical state where the entropy went up, but then at some point it started going back down again. And this is Hawking's famous argument for information loss. It seems like at the very end here, if we just forget about this because it's no longer connected to anything, then the universe that we're left with has gone from a pure state to a mixed state. It's broken the unitarity of quantum mechanics. We can actually, with Page's argument in mind, make this a bit more precise. So this thing should always have a big question mark over it. Who the hell knows what it really means? Because this last little bit of evaporation we lost semi-classical control. Quantum gravity just went completely haywire. But even if we just look at maybe when we've 75% evaporated or something, black holes lost 75% of its mass, then we still have this thing that in typical states, it should have started going back down halfway through the evaporation when the size of the system we were looking at got bigger than the size of the system it was entangled with. Okay? And based on other arguments by Hawking, and also just based on so we know the energy of a black hole, it's just its mass. We know the temperature of the black hole, it's the temperature of the Hawking radiation. With those two things, you can compute the entropy of the black hole, and you find the famous Bekenstein-Hawking formula that are equivalent of log dB, the sort of number of microstates of the black hole, is the area of the horizon of the black hole divided by 4 times Newton's constant. And so we can see that at a certain point, the seeming thermal entropy of this Hawking radiation is going to become bigger than that area of the horizon over 4G. And at that point already, if this was going to be an ordinary unitary quantum process, it should start coming back down. Okay? And our expectations from this calculation are that basically it should only start coming back down when it needs to. That the density matrix being maximally mixed, the entropy being thermal, is completely consistent, is what we should expect to see as long as it's consistent. But then when it becomes bigger than the size of the sort of rest of the system, then it has to start coming back down. So this gives us the famous Page versus Hawking expectations for the entropy of the Hawking radiation, the function of time. So in Hawking's picture, then this just goes up and up and up. It goes up more steeply over time because the black hole gets hotter, it emits more radiation, more entropy. But then we also have this separate curve. So this is the Hawking curve for the radiation. This is the Bekenstein-Hawking entropy. And the Page curve for a black hole is just the expectation that the entropy of the radiation should follow the Hawking curve as long as possible, going up. But then at the last minute, it realizes it's about to violate unitarity, and then it should start coming back down. Okay? Exactly as we saw happen for the typical state. Any questions about that? Okay. So let's now try to take this. So this naive Hawking picture of the evaporation seems to go wrong 50% of the way through the evaporation, even though it seems it should be under control until the last few qubits of Hawking radiation, when the black hole gets down to some sort of fixed order 1 size and comparable to the Planck scale. So the sort of old story, I think people would have maybe said, is that this picture is just completely nonsense after the Page time. So this is the Page time where the Hawking and Page curves diverge. And then something needs to change so that this state of the Hawking radiation starts changing. And at some level, that's obviously true. Like if you just really take this state literally, then it just becomes wrong. But of course, we know that this state is not exactly true, right? This is some perturbative approximation where we sort of, just only take into account quantum gravity effects to basically update the size of the black hole as it loses energy, and otherwise treat gravity as switched off. And of course, you'll always have corrections to that will change the story slightly. But the question is whether they can change the story a lot. And naively, they don't at this time. Except we have to be careful about what this story is actually telling us about, what we can safely use it to compute and what we can't. Okay? So if we think of this as giving us an answer for the density matrix up to some small trace norm error, then this thing clearly becomes wrong. On the other hand, if we just think of it as a way to compute, for example, individual matrix elements of the density matrix, or the expectation value of some simple operator acting on the radiation. You can think of this as like measuring the expectation value of some particular Pauli operator on our typical state. Then we already saw that that remains self-averaging as long as dB is pretty big, i.e. as long as the black hole is relatively big, and so we think we have semi-classical control. So if this is only supposed to be a picture that is telling us how to compute simple observables or matrix elements of the density matrices or things like that, then there's no reason to assume, at least so far, that it has to go wrong. Okay? Any questions about that? Because this is sort of a key conceptual point. Yeah, if we really take the structure of this picture literally, that we have a tensor product of this radiation far from the black hole with stuff in the interior of the black hole, and each of these things, there's no correlation between the individual Hawking quanta, and they're just entangled with the interior, then it clearly something radical has to change. But if we only take this as some tool that lets us compute expectation values or matrix elements for this radiation, then potentially it could still be fine as an approximation. Okay. That's sort of already worked very well to say, like, oh, maybe this thing is just really hard to compute, but it doesn't like actually help us do so. So the question is, if we can't trust this as a computation of the entire density matrix up to small error and trace norm, then is there any way we can still do a control calculation of this entanglement entropy curve? And the answer, fairly obviously from looking back at our random state calculation is sure, why not? Right? We know how to do that computation. All we do is let's forget about the entanglement entropy for now. Let's just think about trace rho squared. All we had to do was take 2 copies of our state and then compute the expectation value of some simple operator that took the system we were interested in and swapped it over between the 2 copies. Okay? So let's do that. Let's do that for, so we didn't do the same computation. I'm going to start with sort of the really baby version. So this is now a trace of rho r squared. It's the density purity of the radiation. Let's just do it with this very final picture where the black hole has completely evaporated. Okay, the one that we don't really trust, but it makes things simpler in some ways because we then think the answer for this should be literally 1. Okay, so to compute this thing, we first need to compute psi, and then we need to swap over the 2 copies of the radiation between the 2 copies of psi. Okay, so psi looks like this. We have a load of thermal radiation in each one, and each thing of thermal radiation is entangled with its own sort of relic black hole. It's now completely evaporated. Okay. So now we just take all this radiation here and swap it over with all this radiation here. Now in quantum field theory, we would have a genuinely different state, right? So we would have a state where this left-hand Hawking radiation is now entangled with the right-hand relic black hole and vice versa. Okay? And the reason that would be a different state is because in quantum field theory, sort of each point in space is fundamentally distinguishable. So if you have a state where there's a particle at x equals 0, and you have a state at particle at x equals 10, then those are just different states, even if they're related by some nice symmetry. Okay? But we're not doing quantum field theory, we're doing quantum gravity. And And in quantum gravity, there's no coordinates are not real. All that's real is the space-time geometry. Okay? So before doing the swap, we have a load of Hawking radiation entangled with a black hole and a load of Hawking radiation entangled with the relative interior of a black hole. After doing the swap, we have a load of Hawking radiation over here entangled with the relative interior of a black hole. We have a load of Hawking radiation entangled with the relic of a black hole. There's no difference between those two descriptions that I just said if there's nothing that distinguishes these two interiors of the black hole. Like geometrically, they look completely identical because we prepared those two states in exactly the same way. We swapped everything over, so there's no difference between the two states. So naively, it seems like this swap hasn't done anything. But then if this swap hasn't done anything, then that tells us that the trace of rho r squared, which is just the expectation of this swap, is equal to 1, i.e., despite looking like it's in a completely thermal state, if we try to do some observation, if we try to do some measurement to actually tell whether it's in a thermal state or not, then the universe wants to tell us, no, actually it's totally pure. What are you talking about? So this argument was essentially made in almost exactly the form I've described back in the early 1990s by Strominger and Polchinski. But I'm not sure how much they even believed it themselves, and sort of the reason they didn't is that this is some picture where we totally lost control and who knows what's going on, and so it feels very speculative. Okay? What we would like to do is some analog of this calculation where we sort of stop the evaporation earlier. We only look at some radiation that comes out at early times and not sort of all the radiation that ever comes out, including the Planckian temperature stuff where we don't know how to compute things, and just swap that early radiation. Okay? And that's what Polchinski and Strominger didn't know how to do, but now we do. So let's change this diagram so that now the black hole is small, but it's still there. Okay. Now let's do the same thing where we swap over this radiation. And now the swap has definitely genuinely changed the state, which is good because we don't expect the state of the radiation to be pure at this time, right? But now we swap this over, then if I erase these blue lines, now this stuff is entangled with this and vice versa. And there's no way you can say that's the same state because this one is connected to this stuff over here by the horizon, and this is connected to this stuff over here. Okay? So if you treat the topology of space-time as a totally fixed thing, then these are just very different states. They have some small overlap because that is basically the sort of naive Hawking answer of trace rho squared of the radiation. But it will get really, really, really small, and it will keep getting smaller the more radiation you have, because there's more stuff you've swapped, and it's more entangled with the interior of the black hole. But again, in quantum field theory, the topology of space-time really would be fixed. But in quantum gravity, we don't expect that it is. We expect that in general, we should be sort of summing over all topologies in a gravitational path integral. We should be allowing sort of anything that can coherently happen to happen. That's sort of a first principle of quantum mechanics, phrased in a very heuristic form. And so we should allow dynamical processes that have the effect, basically, of cutting this and cutting this and switching these two interiors over and then gluing them back on. Okay? That is something that can happen in quantum gravity. I'm going to describe it in a much more precise way for a moment, but that is a thing, and it will end up being described by essentially exactly the same sort of space-time wormhole that Douglas was talking about in his talk a couple of days ago now. Okay? So this is a very unlikely dynamical effect. These black holes are big classical objects. We don't see space-time sort of rejiggling itself around us all the time. This is some tiny probability thing that occasionally happens. It's some non-perturbative gravitational instanton effect. But it can happen. It happens with some probability that we'll call P wormhole. Turns out this thing is going to be roughly e to the minus a horizon net 4g. Okay, so now let's think about the expectation of the swap operator. This will have two contributions. The first contribution comes from when the wormhole swap hasn't happened, right? So that has basically probability 1 of happening. But if that wormhole swap hasn't happened, then this state looks very different to the state we started with. Okay, and so the expectation of the swap operator will be very small, and it will be, I'll call it like e to the minus s2 Hawking. It will be Hawking's answer for the second Renyi entropy of the radiation. But we also have to take into account the part of the expectation that comes from the tiny probability that this swap did happen. That has to be multiplied by P wormhole, because it's only a tiny, tiny amplitude of this state where it happens. But if that swap does happen, then now we've swapped over not only the radiation, but also the stuff inside the black hole. So now the state after doing all this swapping is basically the same state that we started with, right? We again have radiation on the left entangled with the black hole on the left, radiation on the right entangled with the black hole on the right. So if this happens, then the expectation of the swap operator is basically 1. And by definition, basically, after the page time, then this thing will actually be bigger than this thing. And in particular, it will start getting bigger over time. We're seeing the radiation become less high entropy. Okay? The confusing thing, of course, is that where this computation seems to be coming from is this weird dynamical quantum gravity effect, where these two black holes that are completely disconnected from one another somehow spontaneously interact. But if we just look at the answer, then this is exactly the answer we would expect for some unitary quantum process. Okay, great. So that's a sort of very, yeah.
Start, structures, Hilbert space, you make the argument, and then you introduce a new argument that says, okay, put quantum gravity, and this changes things. So is it possible to put quantum gravity from the beginning and make it in a systematic way?
Yes.
You have to argue.
Yeah. So I think that's hopefully what I'm about to do next. I think we'll be doing exactly that. If you still feel I haven't done so after, towards the end of the talk, then complain. Okay. Yeah. Any other questions at this point? So that's basically the rest of this talk is going to try to make this story like a more concrete and rigorous. Okay. And in particular, we're going to do a completely rigorous calculation of it for a very simple model of a black hole and Hawking radiation. And then I'll hopefully have time to explain to you what we can and can't calculate for sort of a realistic 4-dimensional black hole actually evaporating with the quantum fields present in our universe. Okay. So the model I'm going to present is very closely related to stuff Douglas talked about. Let me maybe define it over here. In particular, it's going to be 2-dimensional. Okay. So the great thing about 2 dimensions is you can draw both of them on the board. All of the features of this model are basically designed for being able to represent it on a blackboard. So that's why it's good. So we're going to take a 2-dimensional black hole. So we have 1 dimension of space, 1 dimension of time, both be shown on the blackboard. So it's going to look very like what Douglas was showing. So this represents time going upwards, space going outwards. The only difference is the Douglas's ones have 2 sides, and I want to make mine one-sided again because I want it to look like a real black hole in that sense. So in sort of higher dimensions, the way you have a one-sided black hole is sort of the spatial directions pinch off and come to an origin, right? If you only have one spatial dimension, then you can't have sort of the origin of a sphere. But you can do the next best thing, which is you can just have some point where you say that space ends. So this is called some fancy name. It's called an end of the world brane. But this is just saying this is the end of space. You can picture there being the like star there, right? So this is the star, and then there's nothing beyond the star. Okay, but literally it's just some line in space that has some dynamics that just say there's nothing beyond this point. Okay, so great, we have a black hole. The next thing we need is Hawking radiation. Just like the trouble with real black holes is they have 4 dimensions and you can't draw them on a blackboard. The trouble with Hawking radiation is that it's a Lorentzian process. And then when you start computing like the trace of a density matrix squared, you have forwards time evolution, you have backwards time evolution, and you need to represent them differently, and it gets hard to draw on the blackboard. Okay? So again, I want to be able to draw things on the blackboard. So I'm just going to do something simpler than Hawking radiation that will let me make everything Euclidean and draw it on a blackboard, which is I'm just going to let this end of the world brane have different states. And the different states of this end of the world brane are just going to represent the different states of the Hawking radiation inside the black hole. Okay? So I'm just going to let this end of the world brane have a set of orthogonal states I. And so I'm going to call, it's white. I'm going to call this state of a black hole with this end of the world brane in state I. I'm going to call that psi I. Okay, so this is my very simple model of the black hole with its interior mode sitting in some particular pure state. But the interesting thing that happened in this very heuristic picture of an actual evaporating black hole came about when we took those interior states and we entangled with them with something outside the black hole. And in particular, when we try to create so much entanglement that it was like bigger than the entropy of the black hole. Okay, so let's do that. Again, rather than having some dynamical process that's going to create that entanglement, I'm just going to consider by hand some state that I'll call capital psi that just has that entanglement. Okay? So capital psi is just going to be sum over some large number of these states psi I, so superposition of different states of the end of the world brane inside the black hole, entangled with some state I that's just going to be in some arbitrary reference system. Okay, so the Hawking radiation here was far away from the black hole, but it was fundamentally sort of inside the space-time. Now my sort of analog of Hawking radiation isn't going to be in the space-time at all. It's literally just going to be some other quantum system. Okay, it's just going to make it simpler to deal with. It's not going to fundamentally change the story in any way. Okay. So now we're going to take this state psi. We're going to compute its reduced density matrix on this reference system R. Okay, so let me just write that down. So rho R is just going to be, take this thing and trace over the black hole B. So what is that? Well, we get 2 factors of 1 over square root k. We have a sum over I, and we have a sum over j. And then we have psi j, psi I, times ket I, bar j. Okay. And then we want to compute trace of rho r squared. So take this thing squared. So we have a 1 over k squared. And then we take the trace of this thing squared. That gives us some some delta functions, because it's an orthonormal basis, and we end up with just the sum over ij of the norm of psi I psi j squared. Okay, this is all completely standard quantum mechanics. Now all we need to do is do a gravitational calculation of this thing. Okay, so this was our Lorentzian picture of the state psi I. The thing about a Lorentzian picture is it doesn't let you sort of prepare the state from scratch. That's what Euclidean path integrals are good for. Euclidean path integrals prepare states. Lorentzian ones evolve states. And the sort of Euclidean version of this, if I analytically continue, turns out to look something like this. So this is, again, the same boundary of spacetime, but now it's Euclidean. But now this thing, rather than just sitting inside the black hole, sort of comes out and hits the boundary. Right, one way to think about it is if we didn't have this end of the world brane, we'd have some other Lorentzian boundary over here, right? But then in the Euclidean picture, as Douglas said, explained, those are connected in a disk. And so that left boundary is sort of over here, right? So this is sort of a part of the disk gets chopped out by this end of the world brane that just sits somewhere between the two boundaries. Okay? So this gives us some way, this Euclidean picture basically computes psi I psi j for us. So psi I psi j can be computed by just doing a Euclidean path integral with boundary conditions that say there's an end of the world brane in state I down here, and then we have some boundary of a particular length. It depends on the temperature of the black hole. And then we have an end of the world brane in state J up here. Okay? And the end of the world brane has to stay in the same state, and so this actually gives psi I psi j 0. It's very slightly more complicated than that, in that we need to normalize our state. So, sorry, if we assume that psi I is the normalized state, then we need to divide this by the square root of psi I, psi j, psi j. So this is j, and this is I. Okay? So it's just the usual thing of path integrals do not prepare normalized states. Okay. So now let's compute this thing, which is just a sum over things that look like psi I, psi j, psi j. So 1 over k squared, sum over I j. Have our Euclidean black holes. That's in I here, j, j. And then we need to divide by this thing squared. So on the bottom, we just have, again, basically the same thing, except now it's I, and j. Okay. So this is seemingly a very simple calculation. The end of the world brane has no dynamics. So if it starts in state I up here, then it will only be in state j up there if I is equal to j. So this gives us two factors of delta ij. That makes that double sum over I and j just as a single sum. The rest of the terms vanish. So that single sum gives us one factor of k. Cancels out one of the k squareds over here. That gives us 1 over k. And then we need to account for evaluating the rest of this path integral. But other than the I being equal to j thing, that's exactly the same as this one down here. So they could just cancel out. Okay? So we got the answer of 1 over k, which is exactly what we should expect for a maximally mixed state of the reference system, which is indeed exactly what we prepared here. Except there's one thing we haven't taken into account, which is that we're just doing quantum gravity here. So when you do a quantum gravitational path integral, the geometry of spacetime is dynamical. All you're really allowed to fix are the boundary conditions. That's all you're ever allowed to fix in any sort of path integral. And so the boundary conditions say that there should be an end of the world brane here in state I and one here in state j, but they cannot tell you that this one has to be connected to this one. Okay? So in general, we should be summing over all topologies and integrating over all geometries that have those boundary conditions. In particular, there is an alternative way that those boundary conditions can be filled in. It just looks like this. Okay? This is again just a disk cut out by, so this is just a disk cut out by one geodesic. This one is a disk cut out by like 2 geodesics, but this is some smooth, nice solution to the equations. It's a saddle point. The interesting thing about it is that now this end of the world brane in state I is connected to another. At the other end still only has to be in state I, and the one that's in state J here only has to be in state J here. There's no reason that I and J need to be equal to one another. Okay? So now this double sum really is a double sum rather than a single sum. The 1 over k squared here gets cancelled out by that double sum, and so we get something that's independent of k. So that tells us whatever the hell the answer we get for this contribution to the path integral is, if we make k big enough, if we take k to infinity, that's going to be the dominant contribution. So that tells us this trace rho squared, no matter how big we make k, is somehow bounded from below. There's only so much entropy we can pump into this radiation system when it's entangled with something inside the black hole. No matter how much we think we're creating, then secretly there's much less than we think. So what is the answer to this contribution? Well, the k's cancel out. So all we have to do is evaluate this disk with sort of 2 geodesics cut into it, which I'll call Z2, divided by 2 copies of a disk with 1 geodesic cut out of it, okay, which I'll call Z1 squared. Okay? So what is this thing? Well, I think Douglas explained in his talk that in 2D gravity, there's a term in the action, the sort of dominant term in the action, in fact, that basically tells you a path integral gets a contribution that looks like e to the chi times s naught, where chi is the Euler characteristic of the 2-dimensional topology that you're computing a gravitational path integral on, and s naught is sort of the main contribution to the entropy of a 2-dimensional black hole. It's not the full contribution, but it's the primary contribution. It's the sort of temperature-independent contribution. Okay, so Z2 is a gravitational path integral with the topology of a disk. So that has Euler characteristic 1. So that gives us an e to the s naught. So just very approximately, this is e to the s naught divided by 2 things, the Z1 squared. Each of the Z1s is also a disk, so that also gives an e to the s naught. So divided by e to the 2s naught. So that gives us that approximately this thing scales as like e to the minus s naught. I said s naught was the primary contribution to the entropy of the black hole. So this is telling us that our first approximation, the trace of rho r squared, once k gets bigger than e to the number of e to the Bekenstein-Hawking entropy of the black hole, this thing sort of saturates. It doesn't keep getting smaller as we make k bigger. Instead, the purity just has this lower bound that's roughly e to the minus entropy of the black hole. So again, exactly what we would expect if the entanglement entropy was now equal to the entropy of the black hole. If we're getting some sort of page curve thing where when we try to create more entanglement between outside the black hole and inside, we don't actually create that entanglement and it just saturates equal to the entropy of the black hole. Any questions about that calculation? Does that maybe somewhat is
So I just feel something that I guess that included is important, but you have a copy of a system.
Yes.
And then you want to compute the reduced state, and then so for that you make an auxiliary calculation, you add another system, copy the system, and in principle the system should be independent.
Yes.
But when you do that, then you say no, because of quantum gravity, and I
Yes.
I have now to connect them. And
Yep.
it's a little bit artificial. The fact that you add something artificially connected But you're saying that these are the rules of the game, that whenever I would put more systems and I would be independent, that it's like a mathematical construction, then I have to take different rules and I have to just, in the path integrals, consider even like exchanging.
Yeah. So let me make a few comments there. The first is, as far as we know, in some ways it would be artificial to not allow these sort of connections. Right, let's say that instead these two black holes were in the same space-time, they were just a billion light years apart, but they're in the same space-time. Somehow you've got to say that connections between them aren't allowed if they're too far away or something. Like the sort of simplest, most naive rules of trying to do quantum gravity are just anything can happen. You are completely right that in this case, let me, yeah.
If I trace of rho square.
Yes, yes, yes.
Rho square is not the same rho.
Yes, this is completely right. So, yeah, another way of stating this is this is the correct rules for computing this observable, the swap test observable. Like this, the most naive, obvious rules. But yeah, the point is that this thing, just trace rho squared, as we conventionally think about it, it's just one row. We could have just somehow exactly computed rho if we knew the exact rules of the game. And then it should be the case that then we can just plug that mathematical formula in and square the matrix and take a trace, and we should get an answer. There is an open question. So there's sort of two possibilities. Okay, one is just all of this stuff involving multiple copies is nonsense. I don't think that's plausible because it just gives too many sensible answers. Like it's really trying to give you the sensible answers for unitary theory on one copy. Okay, so that seems very unlikely. But there are two other possibilities for like what would happen if you really did the exact one copy calculation. Okay, the first is that somehow there's effects that are missing that somehow give you another way of getting the same answer. That doesn't involve any wormholes, but there's some other story you can tell, but it ends up by some magic being exactly the same. The other possibility is that doing it that way would genuinely give you a different answer than this two-copy thing. And how could that make sense? It could make sense if gravity isn't a unitary theory or single unitary theory, but instead is implicitly an average over unitary theories. And then what you're proposing doing would be computing the density matrix, which is this average over unitary theories for a single copy, and then computing trace rho squared of the average, whereas what this thing is doing is computing an average over trace rho squared. And so those are just different things if you have some ensemble. So that is also an open possibility. I think we just don't know with confidence what the right microscopic interpretation of quantum gravity is to answer that question.
The consequence that we have average quantities even in a single case.
Yeah, so I mean, then you have a question of if gravity is computing an average, do we live in the average or do we just live in one of the elements of the average, but it like looks like the average, and so that's why we see gravity. We don't know. I'm saying these are some natural rules for computing these quantities that involve multiple copies, and they give very sensible answers. There are a lot of open questions about how to interpret it more broadly. Okay. Great. So let me just have a quick drink. Yeah. So, sorry. In this case, when I connects to J, then it is equal to 0. So this is a confusing thing that relates to what we were just talking about. Of if we just computed psi I, psi j, then the rules of the game tell us that the answer is 0. But if we compute the norm of psi I, psi j squared, then we get an answer that's non-zero. The reason that's consistent is in this case, this very simple theory is actually computing the average over some ensemble of finite entropy theories. And we know actually what the ensemble is in this case. The open question is whether like real theories of quantum gravity in 4 dimensions and so on are behaving the same way. Like in this case, we can do exact calculations, so we know it has to be an average. But in 4 dimensions, we sort of don't have enough control over anything to tell if it's an average or if secretly if you exactly computed the density matrix and took into account all these tiny 1 over d effects, then you would actually somehow get the same answer just in a different way. Great. Okay. So this thing is actually not exactly e to the minus the entropy of the black hole, or at least it's not e to the minus the entropy of the black hole at the same temperature as we started with. But that's sort of fine, because trace rho squared will, it's a thing that's very sensitive to the distribution of eigenvalues, in particular to very large, atypically large eigenvalues. So we don't expect it to be given by the sort of average entropy of the black hole in the same way. So let's try to compute something a bit better, namely the actual entanglement entropy. So we're going to do that the same way we did it for a typical state. We're going to first compute trace rho to the n for integer n, and then we're going to try to take that answer and do some very dubious maths and analytically continue to non-integer n and take a derivative at n equals 1. Take the limit n goes to 1. Good. So let's do the same calculation, trace rho r to the n now. It's very similar, except now rather than 2 copies, 2 inner products, we have n inner products. So draw them. Just draw 4. And we have n of the world branes, each of these things. And rather than it being sort of the norm of psi I, psi j, it's more like psi I, psi j, psi j, psi k, psi l, so on, and then back to psi I. So I'm going to schematically draw that by doing a dotted line here that says this end of the world brane has to be set equal to this end of the world brane. Okay? And then we're implicitly summing over things. So for example, these two are both equal to I, these two are both equal to j, these two are both equal to k, these two are both equal to l. And then we have a 1 over k to the n at the front. And then we need to divide by just the one black hole. I'll just call this divide by z1 to the n. That's the normalization factor. Okay. So just like in the typical state calculation, in general, when k is, say, roughly equal to e to the s naught, then there's now a more complicated set of topologies that can contribute here. In fact, the topologies that can end up being significant are what's called all the planar geometries. They're actually in one-to-one correspondence with all the permutations that can be significant in the typical state calculation. There's really an exact match between different topologies in gravity and different terms in that calculation. That's really why I did that calculation. I'm not going to talk about that now. It's a very nice story. You can read the original papers for it. But I'm just going to consider, just like we did in the typical state calculation, the 2 cases. Firstly, when k is much smaller than e to the s naught, and then when k is much bigger than e to the s naught. Okay, so when k is much smaller than e to the s naught, then the dominant contribution is going to come from the thing that has the largest Euler characteristic. So basically having as many disks as possible, because each disk gives us a factor of e to the s naught, so we have as many as possible, and we get something big. And the way you have as many disks as possible is you just connect the boundaries up like this, and so we just have n copies of z1. Okay, so this then gives us 1 over k to the n z1 to the n times z1 to the n times, but now, so this index has to be equal to this index, which then has to be equal to this index, because they're connected through the end of the world brane, equal to this, so on. All of the indices have to be equal to one another, so we only get one factor of k from summing over them. So we get a single factor of k here, so that's equal to 1 over k to the n minus 1. Okay, so in that regime, so this then implies that s rho r is equal to the limit as n goes to 1 of log of 1 over k to the n minus 1 divided by 1 minus n. That's just equal to log k. Okay, so this is the sort of obvious Hawking answer. The entanglement between the reference system and the interior black hole is just, it's maximally entangled with k possible states, so it's log k. Okay, the second case is, of course, when k is really, really, really big and way bigger than e to the s naught. In that case, the largest contribution is going to come by sort of letting each of these different end-of-the-world brane indices be different, right? So not forcing any of them to be the same by being connected by end-of-the-world branes. The only way we can do that is if this end-of-the-world brane connects to this one, this to this, this to this, and so on. It's what's called the pinwheel geometry. It's sort of some multi-boundary space-time wormhole where sort of all of the different interiors get swapped between the different copies. So I maybe should have made a comment there that maybe wasn't clear to people that this geometry you can think of as there's this end-of-the-world brane in I in copy of the black hole 1, and then J in the other one, and then there's some space-time wormhole that swaps the two over, and that's why they don't connect, they're not forced to be equal to others. So it's a sort of concrete realization of that very heuristic picture I told at the beginning, earlier in the talk. Okay, so in this case, it's a multi-boundary space-time wormhole. So it's like the interior of black hole 1 gets swapped over to 2, and 2 to 3, and so on in some big cycle. Okay, that cycle is the permutation, of course. You know, the dominant permutations were, for the typical state, with the identity in one limit and a cyclic permutation in the other. It's exactly the same thing happening here. Okay, so what's this thing equal to? The 1 over k to the n gets cancelled out by the sum over n independent things. So those cancel, and we're just left with Zn divided by Z1 to the n. Okay, so at the same approximation we did here, then this would be e to the minus n minus 1 s naught. We analytically continued, we'd get an answer of s naught. So that's pretty good. But it turns out we can actually do better. And I've got about 15 minutes left. I think that's enough time for me to do better. So the better thing to do is a very beautiful argument that it will not shock you to discover was originally made by Juan about 10 years ago in a somewhat different context. And it's to directly take this computation and analytically continue the entire computation. So that's going to let us work out the limit of this thing as n goes to 1 without actually needing to compute Zn or Zn explicitly for like n2 or 3 or anything else like that. In this case, we could do it, and it has been done. But in general, you won't be able to. It's hard. But it turns out you don't need to. So the trick is very beautiful. It's just to note that this thing has a symmetry. Has a symmetry where we rotate the pinwheel. Okay? That moves this copy to this one and so on, and just cycles them all around. So what we're going to do is we're going to take this thing and we're going to quotient by that symmetry. So what does that do? It just takes one of these little wedges and glues here to here. So I'm going to draw a picture of that. Okay, so after doing that quotient, it looks pretty similar to Z1, right? It has one boundary, it has one end of the world brane that just connects the two together. Looks almost the same. The difference is just that it comes from this point here in the middle. That's the fixed point of this symmetry. So if we go in a little circle around this fixed point, then in Z1, going in a little circle around any point, we'd have that the circumference is 2 pi times the radius, right? The geometry is smooth. But in this case, 2 pi times the radius would be going in a full circle around here. So instead, to go in a circle in the quotiented thing, we just have to go 2 pi r over n. So this thing now has a conical singularity that wasn't present in the Z1 geometry. Okay, I'm going to call this Z1 brackets n. It looks like Z1, except for two differences. Yeah, except there's the conical singularity here, And then there's a branch cut connected to that conical singularity that's just sort of keeping track of the part that actually, in the unquotient geometry, was glued to the next copy over. Okay? Okay. So, now the beautiful trick. Okay, so one's great idea is that Zn is sort of almost equal to this Z1n to the power n. Right? The sort of classical action of some classical saddle almost looks like, of the unquotiented saddle, almost just looks like taking n copies of the quotiented saddle. It's just a couple of tiny differences. In this case, there's really only one difference, which is just at the classical level. Here, we had no conical singularity here. Here, we have a conical singularity. Okay, and so you get some local contribution that just comes from this conical singularity. It turns out that contribution is exactly e to the minus n minus 1 times the area, quote unquote, of that conical singularity divided by 4 times Newton's constant. Okay? And this is the area. So in 2 dimensions, it's really the value of what's called the dilaton, because this is just a point. But in higher dimensions, this would be a codimension 2 surface. And it's really literally its geometrical area that shows up here. Okay? It's the same. The important point is it's the same thing that shows up in the entropy of a black hole. Okay? So that's almost the right answer. In this case, that is the right answer. I'm just going to write something slightly more general. So in general, we could also have quantum fields in this geometry. Okay, and those will also behave differently in the quotiented geometry versus the unquotiented geometry, because in the quotiented geometry, we're just sort of preparing some quantum state on here and then taking its inner product with itself. In this case, part of the quantum fields are getting swapped between the different copies, right? And so this is actually doing some sort of replica trick calculation for the quantum fields in this background. So there's an extra factor. It's actually doing exactly the same thing we're doing here, just for quantum fields in the bulk quantum gravity. Okay, so there's actually an extra factor of trace of rho bulk to the n, where rho bulk is all the quantum fields, all the quantum degrees of freedom that get swapped between the different copies. In this case, the degrees of freedom that are getting swapped between the different copies are 2 things. The first is this end of the world brane, but the second is the reference system that we by hand chose to swap, right? What is rho bulk? For the end of the world brane in the reference system, it's some pure state. So this thing just gives us a factor of a pure state to the trace of a pure state to the power n, so it's just a factor of 1. That's why we didn't need to care about it in this case, but in general, it's there. Okay? So now, we're going to go over here. We're going to use this clever trick to, like so far this is just sort of a rewriting, it doesn't seem helpful, but we're going to use this to compute the limit as n goes to 1. And the crucial thing is that because we're quotiented, there's no reason now that n needs to be an integer, because n is basically just telling you how strong this conical singularity is in the quotiented geometry. Okay, all of these things now make sense for non-integer n. So now we can analytically continue. The limit as n goes to 1 of Zn over Z1 to the n. We just plug in this formula. Limit as n goes to 1 of Z1n to the n over Z1 to the n e to the minus n minus 1 an gamma over 4g trace of rho bulk to the n. And then we make another beautiful observation. This is one of my favorite arguments in all of physics, which is just that at linear order in n, very close to 1, then this is just changing the geometry by, perturbatively at linear order in n. And the whole point of a classical saddle point is that changing things at linear order shouldn't change the partition function, right? That's the whole point of a saddle point approximation, is that the e to the minus s is invariant. So this thing, a linear order about n equals to 1, just cancels out. Okay? Then we're just left with this, and this, taking the limit n goes to 1, is easy. It's just equal to a gamma over 4g plus s bulk, where I put s bulk gamma because it's all the quantum fields on this side of the surface gamma that go through this branch cut and get swapped between the different copies. Okay? The only remaining question is what gamma is. So in general, gamma can also depend on n. So this is gamma 1. What is gamma 1? Well, gamma is just another aspect of the geometry that we need to extremize over when we take a saddle point. So gamma, by definition, is whatever it needs to be to make Zn, and hence also this thing, invariant as we vary gamma. Okay, so we find gamma itself, we find this surface by just looking for surfaces that are critical points of this functional. This functional is called generalized entropy, because it's entropy plus an area that's also sort of an entropy. And what this is saying is that to compute the entropy of some radiation system, we have to look for surfaces that extremize the area of that surface plus the entropy of all quantum fields that are being swapped between the replicas. So that includes both the stuff we're trying to compute and anything else that's sort of behind that surface. And then the answer we get for the entropy is equal to the generalized entropy of that surface. Okay? That was a little technical and complicated, and I didn't have very long. But let me just say, firstly, what happens in this simple case, and then what happens in general black hole. Okay, so in this simple case, this S bulk is just always equal to 1 for any surface sitting here in front of the end of the world brane. So then we just get the n equals 1 geometry, and we just have to look for a surface of extremal area, a critical point of area. What is that surface? It's literally just the bifurcation surface, the horizon of the black hole. And so the final answer for the entanglement entropy ends up being exactly the zero-dimensional area of that surface, which is also the Bekenstein-Hawking entropy of the black hole. So we've exactly derived the thing we wanted to get. Okay, let me end in my last couple of minutes by very briefly saying, what about a realistic black hole in, say, 4 dimensions with the quantum fields we have in our universe? In that case, unlike in this case, we do not know what these, like even the n equals 2 geometry looks like. We do not have an explicit analytic form. We're sort of very confident that it exists. Some space-time wormhole exists describing it, but we couldn't give you the explicit metric of that space-time wormhole or even evaluate its action. I actually think it should be possible in some approximation, but nobody's ever done so because we're all too lazy. But we don't care. We don't care because we have this beautiful trick due to Juan and Aitor Lukowitz that says all we really need to care about is the limit n goes to 1, because entanglement entropy is much cooler than Rayleigh entropies anyway. And to compute that, we don't need to know anything about those extra geometries. We just need to look for these special surfaces that are extremer of this quantity. And if we find one of them, then that tells us that, it tells us that the wormhole solutions exist, and it tells us what answer they give for the entanglement entropy. Okay, so the punchline that will not dramatically shock you, I would guess, at this point, is that such a surface does exist. So we compute the entropy of sort of all the fields, a load of radiation that's come out here. We have a star sitting at the bottom of our black hole. And a surface exists. It exists before the page time and after the page time. It's just only dominant after the page time. that's sort of close to the horizon, where if we sort of take all this stuff behind it, I'll put that in blue as well, then if we try to vary the position of this surface, then the sum of the area of the surface plus the entropy of all of this stuff together with all of this stuff behind the surface doesn't change. Okay? And then that gives an answer for the entanglement entropy that is the sum of that area and the entanglement entropy. So the area is just the area of the horizon. The entanglement entropy is the entanglement entropy of all the Hawking radiation plus all the modes in the interior that the Hawking radiation is entangled with. So that's some pretty small number. So roughly, we just get the answer for the area of the horizon. Let me just end by giving a sort of 1-minute explanation of sort of why it's reasonable that this surface exists. Fundamentally, it's just a computation that can be done, and you can read if you want to. The point is, by symmetry, we basically just have to check two things. We have to check that the sum of area plus entropy stays the same if we move the surface a little bit this way, and we have to check that it stays the same if we move it a little bit that way. Okay? Good. Moving a little bit this way is relatively obvious, because ignoring the fact that the black hole is evaporating, the area just stays constant as you sit on that surface. Okay? So it's actually a tiny little bit inside the horizon. That's basically because the black hole is producing entropy over time. And so you need a surface where if you perturb it this way, then the area gets smaller to cancel that out. If you're a little bit, tiny little bit inside the horizon, then you have a little gradient that will make it smaller. So that part's relatively obvious. The weird part is this part, if I move it outwards a little bit. Because if I move it outwards a little bit, then the area gets gets bigger. It gets bigger by some order 1 amount. And we have a 1 over g in front of this term. G is really, really tiny, so that means the generalized entropy gets a lot bigger. Okay? And so naively, it feels like anything that happens in the entanglement entropy sort of can't compete. The reason that's not true is that as we move this surface back in time, then things exponentially spread out from the horizon. So if this is a fair way back in time, then the amount I have to move this surface to change which fields get included in my region by sort of an order 1 amount gets exponentially small. So that basically means the gradient of this term here blows up exponentially as I move my surface back in time. I just have to move it a time roughly log 1 over g back into the past, and it can compete with this term, and you find that there's a solution that solves all these things. And so that is giving you the answer for the entropy of this radiation. There's really two possible answers. There's that possible answer, and there's the naive Hawking answer, where instead of this being the sort of fixed point surface, there's just no fixed point surface. It's like the case where it's joined up like this, right? You just move them all around and nothing stays fixed. So it's just the empty set is the fixed point surface. That will give you the Hawking answer. The rules are you take whichever gives a larger contribution, i.e. whichever gives a smaller answer for the entropy. So you get the final answer that S rho r is equal to the min of S Hawking and A over g. There we go. We have the page curve of black hole. I think I will leave things there given the time. Any questions? Right. Yeah.
We have time for questions.
Yep.
So in this drive, is there a distinction between the term from the action for the metric and graviton fluctuations?
Yes. So good. So if we're careful about how we're doing this, we treat the metric semi-classically. So we first look for a saddle point solution. Sorry, we first consider all possible background metrics and then integrate over quantum fluctuations around them, both of the matter fields and in principle also the graviton fields. that will then give us an answer that is like area of the background metric plus entanglement entropy of the gravitons and all the other fields, but the graviton entanglement entropy is included in this term. And then we have to solve for the semi-classical Einstein equations, basically, to know that that classical background metric is exactly the right thing. And again, the energy of the gravitons will back react on the classical metric, so you have to take that into account as well. Yeah.
Follow up on that. You have a non-metric field that has like a non-zero background value for
Yes,
some reason.
if it has some, say, classical background, meaning that it scales such that it has an order 1 back reaction, then that we should again consider fluctuations about that background. Yes. No. As long as your action is just GR, like fundamentally you can smooth out the conical singularity just by like changing the metric, having some like large curvature to the metric. So as long as you're just doing GR coupled to some matter fields, then you won't get anything else. What will change things is if your action includes higher curvature terms, which in principle it should. So things like the sort of curvature squared, rather than just Einstein-Hilbert action, that will then give corrections that are known to some degree. Any other questions?
So it's not the same thing.